uh, in California, it's 2 p.m. here, and for Rekha, it's 6 p.m., right? So let's start the second session. This is a session on theoretical and numerical modeling of inertial waves. And we have one invited talk by Rekha Jain, and then we have three enlightening talks. So please, Rekha, take it away. So next speaker is Augustson. So Carl.
Hello, everybody. Can you hear me?
Yes, I can hear you. How are
Perfect.
you? Okay. So please go ahead, and we will wait for Rekha to reconnect and
Sure. Well, this is kind of a direct continuation of what Rekha was talking about. So Brad and I have been looking at what causes thermal Rossby waves and equivalently their convective mode, the convectively unstable modes, to tilt in radius and longitude. And so this is kind of continuing work from Boussy's work from almost 50 years ago, where we were looking at a particular set of modes. Let me minimize this guy. So as Rekha was talking about, if we look at this F-plane model, you can find a whole suite of modes and their overtones, including these Boussy modes, which have no latitudinal nodes, the Roberts modes, which do have a latitudinal node, among many other modes. On the left here, we have a whole suite of eigenmodes from a sphere. So this is a Bousson-esque sphere. So there's no density stratification, anything like that. It's just uniformly rotating. There's no differential rotation. And you can see a lot of these same branches. We have the Boussy modes here. We have the Roberts modes and many other inertial modes. The ones close to the geostrophic modes at zero frequency are the convectively unstable modes, which have a structure that is very similar to these Boussy, to the Boussy modes. So the question that we wanted to address is, can we, in a simple modification of the F-plane model, understand where these tilts come from? So what you're seeing here is an eigenmode from one of the Boussy modes at m equal 5. You can see these tilts that I'm talking about. So this is azimuthal velocity. You have temperature structures here in radius and longitude. And here we have the structure in latitude and longitude at near the top of the domain. So similar to what Rekha and Brad found for their F-plane models, these really have only a single node. There's no node in radius for this particular mode. Some of the convective modes that I showed here will have multiple nodes in latitude and radius. So in the simplified geometry of the sphere, so we take this F-plane, but instead of having a flat boundary or the millstone geometry that Rekha was talking about, we include a tilted upper boundary. So this, in general, this can be a very steep tilt, but to simplify the mathematics, because when you remap this domain, you actually end up with some fairly nonlinear coefficients in the reduced system. But if we linearize those, we can actually derive a Schrodinger-like equation to get at the dispersion relationship for these modes. And what we have found is that indeed, a tilted upper boundary can lead to radial and longitudinal tilts. So for parameters that are similar to the Bousson-esque spherical case that I showed, we can have very similar angles of the tilt for this simple F-plane geometry. So really, this does appear to be a boundary-induced phenomenon. And that's all I had to say.
Okay, thank you. So we will have questions at the end.
Okay.
Now we go ahead to Catherine. Hello, Catherine.
Hello, just give me a sec to share.
Yeah. Okay, good. So please go ahead.
Hello, I am presenting new work that will hopefully be out in the next few weeks. The punchline is on the title slide, which is that there's a possibility that we might be able to observe Rossby waves that are living extremely deeply in the sun. So the idea behind the project was that I did a beta plane calculation of radial eigenfunctions in a thick shell and discovered a couple of different things. The first is one that we knew before, but it's a bit more obvious in this calculation, which is that there are definitely two cavities that can support Rossby waves in the sun, one in the convection zone and one in the radiative interior, and that's what's being plotted on this figure. The convection zone modes are very, very close to the top. They're in an extremely small cavity. This is calculated for Model S, by the way. So the radial profile, who knows how correct it is, but for Model S, you get convection zone modes very close to the top, and then you get radiative modes in the radiative interior and below. The local dispersion relation that I find is extremely similar to the shallow water case, with the difference that our kind of separation constant here is numerically calculated, which is fine. And then if you go ahead and calculate the radial eigenfunctions in vorticity specifically, which is what we would care about for an observation for these modes that live here in the radiative interior, you get a plot that looks like this. And the important thing about this plot, each of these lines is a different radial order. So blue is no nodes in radius, orange is 1, green is 2, and red is 3. This line in the convection zone is not 0, and it is relatively constant, and we understand why. But the idea here is that because this is not exponentially decaying in the radiative interior, or in the convection zone, we might be able to see them. There are 3 asterisks here. One is that this was a calculation done in Cartesian geometry, and there are geometrical effects that aren't captured here, although I think I understand what those are. One of them is obviously latitudinal differential rotation is not captured in this model, and radial differential rotation is not captured in this model, which is something that I would like to look into. But this is definitely a direction that I'm going to be going in. The final slide that I just want to flash is that I've calculated the frequencies that we would expect for both convection zone modes and radiative interior modes of varying radial order. On the left is what, if you had kind of infinite resolution at your disposal, what you could get as a line profile for these modes. But if you take the frequency resolution that's more or less available to us with observations, they all get kind of smushed together. So even if there are multiple radial orders present of all of these modes, it's extremely possible that we have absolutely no idea. And that's it for my lightning talk.
Nice, thank you, Catherine. So questions, I have some, but let's wait to the discussion session.
Yeah.
So Ankit, please.
Perfect.
Hello, let me try to share my screen. Hopefully this goes smoothly. And can you see my screen?
Now I can, yeah, please go ahead.
Okay, so I'll talk about a sort of a fairly simplified system which has very little to do with the sun, but which provides a very simplified system to look at inertial modes and many different properties. So this work I did during my PhD, so 7-8 years ago now. So there's a very simple system called the spherical Couette system, where you have 2 differential rotating spheres that give rise to a sort of shear layer, and the shear instability of that layer gives rise to these nice inertial modes, and eventually leads to turbulence and whatnot. And so you can see here is a movie of, you get this m = 1 inertial mode, so Rossby mode in the beginning, which turns into this this large scale and 2-2 or 3-2 Rossby mode. And then because you're changing the differential rotation, you can study its effect. And as I was seeing Gustavo's talk, this is exactly what struck my mind, that from right to left here, this is increase in differential rotation. And you can see how this mode slowly gets twisted, especially inside the tangent cylinder. There's the same mode that is getting twisted, and as well as it's changing its frequency. Then, of course, you can impose convection on top of it, and you can see how it coexists with this large-scale inertial mode. And you can see for 10 times supercriticality in convection, you see a clear signature of the mode near the poles, while near the equator, you see more of the convection. And then for 30 times supercriticality, even though you see less of the large-scale signature, you still see sort of a clear signature of the mode near the poles. Of course, then there's the effect of magnetic fields, which I studied briefly. Very different kind of field, not toroidal, but more of an actual colloidal field. But what was interesting to me was, if you, this is a rather complex plot, but if you focus on the blue and the red lines, is for this same large scale mode, that the blue line is without magnetic field. There's the kinetic energy with time, and the red line is with magnetic field. So you can see with magnetic field, you have a much larger growth rate and then a much larger saturation of energy. So this system, as I said, is a very simplified system that allows you to study all these things in isolation, and then you can pick how much this is relevant to the sun and so on. Thank you very much.
Thank you, Rekha, and thank you all the speakers of this session. So now we are in the time for discussion, and I will start with an online question, a question in the chat. It was done to Rekha by Peter Gilman. And I don't know if Peter is in the audience and he wants to do the question. Otherwise, I can read it.
Oh, where is the question? Can you please repeat it?
So the question is, in the assumed aging function phi. Oh, Peter is online. So
yeah, if you go back to your original formulation, I got confused early. Let's see, where is it here? Where you were defining wave numbers. It's even earlier. Yeah, okay. Assume plane wave solutions. You use notation that I found confusing. You've got an I square root of -1 in front of the kx, but not the ky. So,
oh, sorry, there should have been, yeah, there should have been a bracket. I'm sorry.
A common solution is to have exponential in y,
yes,
and periodic in x. But you're saying this is periodic in both x and y.
So first we did these calculations with the plane wave solutions and found the retrograde and the prograde propagating. Only the prograde propagating were the radially trapped. And then it is this other model wherein no longer have the, so this model was just, I was just showing to for these two terms that you could have in classical inertial waves in the latitudinal direction, and also you can have thermal Rossby wave. But the actual model results I was showing was for the Millstone one, where we I think this one, yeah. So this is the cylindrical model that we take. So now the latitudinal wave numbers are discretized, so they're no longer plane wave solutions.
Right, but isn't it also the case that if you took the eigenfunction as you defined it, with no I in front of the ky, you would have gotten another class of solutions which have exponential.
No. So there should be a bracket. It was in front of both.
But my point is slightly different.
Mm-hmm.
Having no I in front of the ky potentially gives you another class of solutions where they decay exponentially or grow exponentially in latitude.
Yes,
I think in meteorology those are well known.
Yes, Yes, they are. And in fact, the rotation vector, if you consider this the beta plane approximation, yeah. So then you do get another kind of waves. Yes.
Right. But those are also in principle valid solutions. So it's another
Yes.
class.
Yes. Yes.
I mean,
yes.
I think Kelvin waves fall in that category.
Yeah. Mm-hmm.
But those all involve a latitudinal variation in the beta effect, which we have not included. So there's no coefficients that depend on y in
Well,
this
that just
particular
allows you
problem.
to find the solutions, what by analytical means. I'm just saying, it looks like there's another class here that you could consider.
Which is in the latitudinal direction when you take the beta plane approximation. Yes, I think so this is very simple model where we have done the latitudinal trapping in this way, but the ideal way is the way that you're suggesting, and that those calculations are being carried out. I have some preliminary results which but I have not shown here because I'm not 100% sure if it's done. But yes, you are right that there are other solutions that will come into it when you don't have the plane wave approximation for in KY. Yeah.
Yeah.
So it is so Peter, this is very similar to Glatzmeyer and Gilman paper,
Yes.
except that these are exact solution in terms of Whittaker functions, as opposed to some asymptotic approximations. Yeah.
Right.
Mm-hmm.
All right. So there was another question to Ankit, but it was solved. But maybe it's good to make again the question. So Lucas is asking if the inner boundary is rotating faster in your model.
The inner boundary, at least in the simulations I showed, is rotating in the opposite direction and usually faster.
Okay.
Thank
Depends
you.
on
I
whether
missed that.
delta omega is less than or larger than the magnitude is less than or larger than 1, but it's always rotating in the opposite direction as the outer boundary.
And this was Boussinesque, Ankit?
This was Boussinesque.
Okay, so constant density, right?
Yeah.
Mm-hmm. Yeah, and then there is a 1 million question from Juana. How do we reconcile tachocline, radiative near-surface Rossby waves? Are the near-surface Rossby waves an extension of these deeper layer Rossby waves? Are they different entities? Do these Rossby waves propagate upward from the solar interior to the surface? Does anyone want to?
I think I can say something, which is that we don't know for sure, at least in terms of modes that live in the radiative interior and modes that live in the convection zone or at the very top. Those are two separate families, and whether or not you can actually separate those two out at the surface if they're both there, we're not sure yet. So I know Lucas just had a comment about time and spatial scales, so pass it off to him.
No, please, no. That's just a very rough comment because I was thinking about simulations that it's very hard to comprise these two regions, for instance, like radiative and convection zones, because they have very distinct thermalization time scales and length scales. And I was just following up the DNS comment.
So, Catherine, this I have a question. If
I see that Peter has a question.
I think Peter has a question.
Oh, okay.
I wanted to respond to that the previous question, namely about can the waves be at the bottom be seen at the surface. We did publish a paper on that in Monthly Notices 6 months ago or so. That it's very frequency dependent of the Rossby waves in the tachocline. And as I remember the result, I hope I don't get it wrong, is that the the slow-moving ones can get through. The fast-moving ones are going to have very little amplitude at the top. But there is one class of modes that we might be able to see at the top. It will attenuate, but not to the point where it might not be detectable.
Catherine, these cavities depend on this ratio between the Blume Vaisala and the rotation rate, as the previous words of Jembowski and Kosovichev.
So this particular model, it's just a buoyancy frequency dependence. We didn't vary the rotation rate at all. And so it's unclear to me what that impact would be. And that's future work for me.
Mm-hmm.
I am not familiar with the work that you mentioned, so I would love if you could send me a link.
Yeah, it's 87, Jembowski and Kosovichev. It's a series of 3 papers.
Okay, perfect. Thank you.
Any other question?
Yeah, I have another question actually. So for the people doing simulations, have you seen any evidence of Rossby waves like propagating upwards?
Yes. Yes, but like the rate at which they decrease, I'm still not sure.
I guess it might also be mode dependent. Some of them, like if it's a toroidal mode, it might care less about what's happening in radius compared to other modes.
Something that I noticed was that the ones, at least just from a pure Rossby wave perspective, the ones that were propagating upwards were the ones that were least impacted by differential rotation.
Right. Yeah.
And that they were the ones that were trapped near the equator.
Yeah, that makes sense.
So what about these thermal Rossby waves? Is perhaps the question to Rekha. If I understood properly, the high frequency waves are a combination between the Rossby modes and the thermal Rossby waves. But we observe the Rossby modes, and we don't observe the thermal Rossby waves. So this is because they are very weak and they are contributing somehow, or what's happening with these waves?
Where are we? Okay. So, I mean, anybody's guess, they could be overstable convective modes, so potentially unstable. Or it could be that they are buried so deep in the interior that the amplitude is very, very small near the surface. Or it could be that these, numerical simulations also showing probably don't have enough resolution to show that they are completely nonlinear. Because they do exist in weakly nonlinear calculations. So retrograde and prograde branches are both there. It's just that retrograde branches are only seen, and it's anybody's guess, really, why prograde are not seen. I'm just speculating, but I have no idea why they are not able to observe them.
Is there a particular amplitude of the thermal Rossby waves that give you the observed high frequency modes, or a minimal amplitude of the thermal Rossby waves that you can reproduce the high frequency modes?
So what we are getting from our model is that these are mixed modes. So you have prograde and retrograde branches. And what is observed by Hansen et al. Is only the retrograde branch. Okay. They have only observed it, but looking at the eigenfrequencies, looking at the radial vorticity, because these are antisymmetric across the equator. So that suggests that these are three-dimensional modes, and there should be a prograde as well as retrograde branch. Now, why only retrograde branch is seen and not the prograde is anybody's guess. It could be that these are very low amplitude waves, or their wave cavity is slightly deeper into the interior.
So I want to continue a little bit on this question. So if we look for thermal Rossby waves, what is the best physical quantities we look at? Is it still the vorticity, the vertical component of vorticity, or we look at temperature or intensity distributions? So any thoughts?
So from our model, if one can measure the phase shift between, say, radial velocity and the horizontal velocity, so then that is a possibility, because these thermal Rossby waves in the model are due to stratification. So they do have three-dimensional fluid motions. So if there is a way to measure phase shifts, or if there is a way to temperature, I cannot say for sure, because I haven't these are still sort of around the equator. But it seems like that the phase shift is one way to look at it, or radial vorticity as well, because from our model, that the difference between the higher overtones is that there is a shift. These are highly vertical and horizontally divergent. So all the prograde propagating ones, if you can measure the radial vorticity and the horizontal fluid motions, then that is a possible way to identify the prograde branch. But it is a mystery as to why only retrograde waves are observed and not the prograde propagating.
Okay, thank you.
Yeah.
So Roger?
Roger, you muted.
Okay, can you hear me now?
Yes.
Okay, I just wanted to say that there's a big effect from supergranulation that seems to be missing from everybody's discussion. The supergranulation velocities on the surface are really quite dominant, and I'm not quite sure how you can ignore them and see your Rossby waves. I don't see Rossby waves on the surface, but I do see lots of supergranulation and magnetic effects. I'll be talking about that if you hang on till later this morning. So just wanted to put that on the table, and if anybody has any response, I'd be happy to hear it.
Okay, thank you. I'm sure we will. We're waiting for your result. And Ankit?
Yes, I just wanted to more think a lot of the aspect of prograde versus retrograde waves and what is observed. I think it depends, on what can be observed and what makes it to the surface, of course, but also potentially what gives rise to these modes might also detect which modes are actually selected by the system, depending on what is the onset mechanism.
Sure. Sure, excitation and damping calculations have to be done for these modes, yeah.
For example, even if our very simplified system, depending on how we differentially rotate the spheres, we find prograde versus retrograde modes. So depending on which way the shear instability gives rise to the inertial modes.
Mm-hmm.
So I have another question too. all the speakers of this session. Is there any way of reproducing the high frequency modes without the thermal Rossby waves? And in view of this convective conundrum, I am asking, what's your opinion? Is there any convection in the solar convection zone with larger scales than supergranulation?
Well, I think it's very hard to understand how you get a differential rotation if you don't have something that's more like these thermal Rossby waves. I mean, this is actually a question for the room. We've got a nice mix of people here. Does anyone else know how to get a differential rotation, you know, with the prograde equator and retrograde poles without something that resembles thermal Rossby waves?
Is the lambda effect different from thermal Rossby waves?
I think the lambda effect is just a parameterization of Reynolds stresses, and
Right.
That's right.
yeah.
They come from convection.
I mean, if you look at supergranulation too, it doesn't really care about rotation very much, right?
Right. What about the first question? Any way of getting the high frequency modes without thermal Rossby waves?
I've not seen a way that you can get that without thermal Rossby waves from an analytical point of view. They show up in the linear eigensolver results all the time, but I don't think I've seen anything. I don't think I've seen anything analytical that didn't start from a thermal Rossby wave. But also, there hasn't been very much written analytically about these at all.
Gustavo, if you just removed the compressional beta effect from these models, you would eliminate the thermal Rossby wave contribution, but you would still have the contribution from the Coriolis force that gives you the classic inertial wave solution where you get variation only along the rotation axis. And as soon as you also allow a little bit of longitudinal variation and have a wave number that's not just purely along the rotation axis, you get high frequency waves. They exist both retrograde and prograde, however. It's the asymmetry that's introduced by allowing the compressional beta effect to also exist that gives you this difference between the retrograde and prograde branches.
So, Peter.
Yep. On this convective conundrum business, seeing all this evidence of Rossby waves of various types in the convection zone, it might be useful to try to estimate what is the total kinetic energy in all those waves. It seems to me that it's possible that there's some kind of a partition of energy between what are truly convective cells on very large scales and all these waves. And maybe you can get away with a lower amplitude for large scale convection that's not really been detected, but because a lot of the energy is in these other modes. So you could have both coexisting with a smaller, I mean, the estimates about what the convective velocity should be are based on other kinds of arguments, but it doesn't take into account transfer of energy into other classes of modes. But everything there has to be excited from the temperature gradient going across the convection zone. You know, the energy for all these thermal Rossby waves, all the various inertial modes, has to come from that ultimately as well, just as the convection does. There's some kind of partition of energy among those, and whether you can have, I don't know, half and half, 2/3, 1/3, and that would get you a smaller RMS convective velocity, which maybe hasn't been detected yet at depth. That's the thought I have.
I'd be happy to show a Dopplergram of the surface convection zone, just so you have some context of what it is I'm talking about. If you would like to see that, I have an image I can show.
Do you have it in your presentation, Roger?
Well, it's in the presentation, but you know, at this juncture, it might be of this
Okay. Okay, I think after that, Lauren has a comment too.
So should I share this or not?
Yeah, please. Yeah, yeah.
Hopefully. Sure, it seems like it's not sharing. I'm not sure quite why. No, it wants me to upload it. Okay, well, I don't seem to be. It's a good thing to find out now that I'm not able to show my slideshow, so I can't. I don't seem to be able to share it at the moment. Hopefully
Okay, so we will see it in your talk. Laurent? Okay. So we still have 1 minute. Does anyone want to say something before
I'd
the
like
break?
to make a question to Peter, if you mind.
Okay.
Yeah.
So, do you have any clue about what mechanism can be like transferring this energy, this kinetic energy to these waves?
Well, we did do a paper specific to the surface layer where supergranulation scale kinetic energy of the horizontal motions, which is of course very big, can readily generate by inverse cascade Rossby waves of the classical type. And the model dispersion relation agrees quite closely with the observation. So at that surface, that's what you can get. But deeper layers, it might not work the same way.
Yeah, if I may comment. So this is the kind of work that Jordan Philidet did recently. He used the spectrum of vorticity observed at the surface. So a lot of it is from supergranulation scales, and excited the Rossby modes. And he finds that this basically explains the amplitudes of the modes, right? Another thing that I would like to mention is that in the original discovery paper, we had actually compared the amount of, I mean, we had compared the how much vorticity is in the convection and in the Rossby waves at the scales where they were observed, so less than m of 20, let's say, and it was basically 50-50. Our explanation is that we were estimating a Rhine scale around this m equals 20. So that's the inverse cascade that I was talking about, I guess.
So this kind of agrees with Peter's idea that the energy is being shared?
I think so, yeah.
Interesting. Okay, so we are in the time of the second break, and we have a half an hour, 2 minutes less than half an hour to reconvene. Yeah, so see you in 28 minutes to the third and final session. Thank you.